you very much. It's a pleasure to be here this morning and tell you about some of our recent work. Congratulations to all of you that found the room and negotiated your way up the elevator. You've already passed the first test. I'm going to tell you about recent work on building large-scale quantum networks, and mostly fiber networks is what I'm going to talk about this morning. Okay, so now let's see. Do I have to switch it on? Doesn't it advance? Oh, there we go. Now it does. There we go. So in recent years, we've seen an evolution of quantum communication technology. Until relatively recently, most of the implementations were point-to-point QKD links that could be used for applications like off-site backup. But increasingly these days, we're seeing most of the deployments are what we call the quantum secured network. So that's an ordinary telecommunication network, which is secured by quantum cryptography and also post-quantum cryptography. And that can be used for quantum secure communications as a service for applications in various sectors. And eventually, we think this will evolve into a quantum internet. So a quantum network that can be used for secure communications, but also a much wider range of applications, such as distributed quantum computing and quantum sensing, for example. Now, I can hear my voice fading in and out. Can you hear that as well in the microphone? Is it okay? Yeah? Oh, okay. Some funny effect then, just only I hear. And we've been working in this area, actually, in Toshiba, Europe, for many years, for a couple of decades, in fact. And we've made several significant contributions to the quantum communication field. So, for instance, we made the first demonstration of QKD over 100 kilometers of fiber back in 2003. And more recently, we extended that to 600 kilometers of fiber using a new protocol called twin field QKD, which I'll tell you about later. Also, we made the first demonstration with a secure key rate higher than 1 megabit per second, and later extended that to 10 megabit per second. And we've done a lot of work as well of how you integrate quantum communications into a conventional communication network. So looking at different types of architecture, such as point-to-multipoint type networks, such as are used in the access part of the network. Or studying how we combine quantum and conventional data signals onto the same fiber using different wavelengths of light to carry both signals on the fiber at the same time. And we've always done a lot of work on validating this technology in various field trials and deployments. So we were involved in the first trial of a QKD network in Europe back in Vienna in 2008 as part of the SECO-QC project. More recently, we've been part of a large project in Europe called OpenQKD, which has been building test beds for quantum communications in different cities across Europe and demonstrating various use cases. And most recently, we've been doing a commercial trial of QKD along with BT in the City of London. And again, I'll tell you a bit more about that later. Okay, so now I'd like to tell you about the QKD technology and performance. Then I'll move on to talking about the London network, which we've recently set up. And finally, I'll talk about deployments and use cases. Okay, so after the 2 decades of R&D in Cambridge, eventually we recently launched a suite of commercial products for quantum secure networking. And in particular, there are 2 variants of this product. One which operates with a quantum wavelength of 1550 nanometers, where the fiber attenuation is minimum, and a second which works at 1310 nanometers. So the 1550 nanometer system, which we call the long distance system, it offers operation over the longest fibers. Actually up to 150 kilometers is the specified value, or 175 kilometers is a more typical value. and also offers the highest secure key rates, so specified as 300 kilobit per second at a 10 dB loss, and typically 800 kilobit per second. And then we have a second variant called the multiplex system. It works at 1310 nanometers, so it has a slightly lower key rate and shorter reach. But it has the great advantage that you can operate it on data carrying fiber. So you can multiplex together in the same fiber the quantum signals in the O band and multiple data signals in the C band at the same time. And obviously that makes the multiplex system much cheaper to deploy because you don't need dedicated dark fiber on which to operate the quantum channel. And this figure summarizes the performance of the long distance system. So it shows the secure key rate on a logarithmic scale as a function of the fiber distance. And you can see that for a 50 kilometer fiber corresponding to 10 dB of loss at 1550 nanometers, we have a typical secure key rate of 800 kilobit per second. And that's sufficient for 3,000 AES encryption keys per second. Now that may sound like an awful lot of encryption keys, but bear in mind if we want to build a large-scale network which has lots of users and lots of applications, then we need high key rates on the trunk lines within such a network. And typically the system will work out to around 175 kilometers of fiber or so, corresponding to 35 dB of loss at 1550 nanometers. And even at those long distances, we still have quite a respectable secure key rate of around 0.9 kilobit per second, corresponding to 3 AES keys per second. And this is the highest key rate and the longest range of any commercially available QKD system at the moment. And that's largely thanks to the high rate single photon detection technology that we've developed in this system. Another important performance metric is the ability to combine quantum and ordinary signals onto the same fiber. And here's the results of some trials that we've done recently with Orange Innovation here in France. So we're combining QKD in the O band at 1310 nanometers, along with optical transport in the C band with 60 WDM data channels co-propagating along the fiber at the same time. And these tests were done over different fiber lengths of 20, 50, and 70 kilometers. Here are the results for 50 kilometers of fiber. So with a total launch power of just under 17 dBm, we have a secure key rate of 100 kilobit per second, while co-propagating 60 DWDM 100G channels at the same time with an aggregate bandwidth of 6 terabit per second. So you can see that we can have an almost full C-band of data co-propagating with the quantum signals in the fiber at the same time. And as I mentioned before, this makes the deployment of the technology much cheaper because we no longer require dedicated fibers to deploy the QKD system. So the system consists actually not just of the QKD hardware, which we've been talking about previously, but it also has a software layer as well, the network key delivery layer. And it's responsible for distributing secret keys between any two connected points within the network. It does that by encrypting this global key, which is sent between these 2 points using the local QKD keys for each hop, and also routes the key material through the network. So using that, we can then distribute keys between any two connected points within a mesh network, as you see here. And we can use those keys in a variety of different ways, but most commonly, what we do is we use it along with a hardware encryption module, such as running the AES encryption algorithm. And we can use QKD then to frequently change the encryption key, which is used with our hardware encryptor. And that has the advantage that it prevents cryptanalysis of the data by frequently refreshing that encryption key. Okay, so recently we set up a commercial trial of a quantum secured network working in collaboration with BT in London. So this was launched in April 2022, and it's providing high bandwidth data services secured by QKD and actually other quantum safe techniques as well, including post-quantum cryptography for customers with sensitive traffic. And it's available to BT enterprise customers in the greater London area. And in terms of technology, it's hosted in the core nodes of BT in London. I'll show you where they are in a moment. It uses access tails, which are provided by BT OpenReach by a standard product that they sell for that. Toshiba are providing the QKD, KMS, and the quantum network control technology. And the optical transport and encryption technology is supplied by ADVA. Okay, so this shows a simple schematic of how the London network works. And it consists of a core network owned by BT. And we have 3 core nodes within that core network. So one is in the city area, where there are many financial companies in London. Another is in the West End, where many of the creative industries are located. And then finally, we have a third core, which is in the west of London, in a place called Slough, where there are several big important data centers. So we chose those sites to have access to the largest number of customers. And then a customer can access this service by installing an access tail, which goes from their premise to one of the core nodes. And this access tail is a standard product which is provided by BT OpenReach. They can then, let's say they have 2 buildings in London that they want to communicate securely between. They can then use the network for distributing keys between their 2 premises, and then use those keys for encrypting data using a hardware encryptor between the 2 sites. And of course, we can connect multiple customers to this network at the same time, and the network will provide keys to those different customers simultaneously. Okay, so what's special about the London Quantum Secured Network? After all, we've done lots of trials of quantum communications in the past. There are some things which are different about this, though. First of all, it's hosted in a real operational environment and not in the lab. Here, in fact, you see some equipment installed in a rack in one of the BT central offices. All the equipment is telecom approved. Also, we're using customer tails which are based on a standard OpenReach fiber product. And that's very significant, actually, because any customer can go to OpenReach and have one of those tails installed. So in principle, once we build this network out to a larger scale, any customer in the UK, or even beyond the UK, will be able to use quantum secured network services. Also, we have QKD and data coexistence in both the core and the access links. We've implemented a key management system at every node, and this coordinates multiple customer connections at the same time. And finally, it's closely integrated into BT's network management operations. Okay, so what's coming next? So we've built a metro network in London, and actually we've done similar things in other parts of the world, such as Tokyo. But I believe the next step will be to build national and continental networks. And here we're at a very exciting stage now, because the recent improvements in the performance of QKD technology means that we can now operate with quite high losses of 35 dB. And this means that we can now directly connect the core nodes that you have in a national network, such as the UK, for instance. It has around 20 to 30 core nodes, which are typically placed in the different metro areas where most of the customers are located. And the technology has got to a point now where we can directly connect those nodes, either using standard technology, which has a maximum loss of 35 dB, or using optional superconducting detectors, which can further extend that maximum loss up to around 55 or 60 dB. And this is significant because it greatly reduces the QKD hardware, which is needed to build a national or a continental network. It's only needed at these node locations. And it eliminates the need for any trusted nodes in between these core node locations and less trusted sites, such as communication huts, for instance. And of course, although I've used the example of the UK, this can be applied to other countries as well, such as France, for example. And finally, I'll tell you about some of the things which are coming out of the research lab at the minute, and we hope to bring into the commercial domain soon. So one of those is a technique called twin field QKD, and this is a way to yet further extend the range of a QKD link. You can think of twin field QKD as a kind of primitive quantum repeater. Basically, it involves installing one node in between Alice and Bob, and effectively it doubles the length of a QKD link. Twin field QKD has a similar scaling to a one-stage quantum repeater. So you can see it has a shallower dependence of the secret key rate on distance. And it allows us to achieve much longer distances, in fact, up to 600 kilometers in this particular demonstration, and also to achieve much higher secure key rates for those longer distance links as well. So it will be possible to extend the range of QKD links in the future, and I'm sure there'll be further innovation beyond this. Another very important innovation which is coming, which I think will be a real game changer, is the introduction of integrated photonics to quantum communications. So currently we build all of this technology using discrete fiber optic devices, which are put together into a complex optical circuit. That works well, but of course it's quite an involved process and also has a certain cost as well. What we'd like to do is integrate all of this photonic circuit onto a tiny semiconductor chip, which can be fabricated by standard semiconductor photolithography techniques. And this would allow us to manufacture these systems in much larger volumes and for a lower cost. And I believe this will be very important in the future if we want to build large-scale networks, because in the future, one of those core nodes in the network that I showed you earlier could have tens of thousands or hundreds of thousands of access links. And this technology will have to be able to make this technology in much larger volumes and for a lower price if we want to reach those sort of scales. Now, recently we realized the first fully functional QKD prototype, which is using this QKD chip technology. Here you see a photograph of it. It looks a bit rough and ready at this stage. The sender unit that you see here integrates a quantum transmitter chip. Here you see a photograph of it, and also a quantum random number generator chip, along with some driving electronics inside this box. While the receiver end has a quantum receiver chip, and again another quantum random number generator, and some drive electronics integrated within the receiver side of the system. So this will enable a much wider deployment of quantum networks in the future. And finally, I'll tell you about some of the recent deployments that we've been involved in Toshiba. So we've already spoken about the work we've been doing in the UK with BT. In Southeast Asia, we're up to lots of interesting things as well. So we're building a metro network in Tokyo, similar to that one in London. We've also done some trials with NTT recently. And in South Korea, we've been working with the carrier KT in making a long distance link there. And we've also been doing some work with a startup company called Spectral, who are interested in satellite QKD in Singapore. In the US, we've done some trials in the financial sector with JP Morgan Chase, encrypting blockchain communications. We've been doing some trials with Verizon, and we've been working with Chicago Quantum Exchange in some of the next generation stuff, entanglement-based quantum networking, which I don't have time to tell you about today. And then in Europe, we've also had lots of activities, actually. So I mentioned earlier our work with Orange on QKD multiplexing. We've also been studying quantum software-defined networks with the University in Madrid and Telefonica, quantum-safe 5G networks with Deutsche Telekom, various applications with PNSC in Poland, and finally studying QKD next to railway tracks with a university in Prague. So most of these deployments were as part of a European project, OpenQKD, and this is now led on to the EuroQCI project, which will soon come to its deployment phase as well. And I think that will lead to an even wider range of use cases and applications in the coming years. So finally, what's the outlook for the future? Well, we think a global quantum network in the future will consist of fiber networks in countries and continents. And these will be connected together using satellite QKD in the near term, I believe. So that will be a way to connect these different fiber networks in different regions and make a truly global network. And in the fiber network, so the long distance links will use the current QKD technology and also twin field QKD, and maybe eventually real quantum repeater technology as well. And also very important in this picture will be integrated photonics for allowing us to build lots of low-cost access networks to allow business users to connect to this quantum network. So that's all. If you'd like to learn more, please visit our LinkedIn site. And I can see I haven't left much time for questions, but do feel free to ask a question if you have.
Time for one question, one short question, anybody? And if not, please see Andrew at the breaks or in the exhibition. Oh, there's a question real quick.
Yes, you mean the classical messages, which are sent back and forth as part of the QKD protocol? So we use actually an information theoretic protocol for authenticating those messages, which are used as part of the QKD protocol. And of course, that's very important for the security of the overall key exchange. So it can be proven to be, it's not just, it can be proven to be secure from first principles. It's not just computationally secure. So it's a classical algorithm which is used for authentication.